Hello guys, in this video we are going to discuss the solution of the problem number of good components. So let us look at the problem statement. The problem statement says, given an undirected graph with v vertices and numbered from 1 to v and e edges, find the number of good components in the graph. A component of the graph is good if and only if the component is fully connected. A fully connected component is a subgraph of a given graph such that there is an edge between every pair of vertices in the component. The given graph can be disconnected graph. So for instance, this is a graph which is given to us, and as you can see, there is just one component of this graph which is fully connected, because of which we are returning 1 as an output. Similarly, in the second example, if you see, there are three components of the graph. 1, 2, 7 is one component, 6 alone is one component, and then 3, 4, 5 is another component. Out of these three components, 3, 4, 5 and 6 are fully connected, because of which the number of components or the number of fully connected components is 2, and that is why we are returning 2 in this particular case. So that's about the problem statement, folks. Now let us discuss the solution of this problem. So in order to solve this problem, we need to understand one concept, which is the relationship between the number of edges and number of vertices in a fully connected graph. So the relationship between number of edges and number of vertices in a fully connected graph is number of edges is equals to number of vertices into number of vertices minus 1, and then this entire thing is divided by 2. So let us take few examples in order to understand this. So let us say there is a graph with 3 vertex, and if this is a graph with 3 vertex and if this is fully connected, then the number of edges will be 3. So now over here 3 is the number of edges and the number of vertex is 3 into 2 by 2, which gives equals to 3. Similarly, if you take a graph with 4 vertices and the graph is fully connected, then in that case the number of edges is 1, 2, 3, 4, 5 and 6. So the number of edges over here is 6, which is equals to 4 into 3 divided by 2, which is equals to 6. So this is the relationship between the number of edges and the number of vertices. Now using this concept, we are going to solve this problem. So what we are going to do is, for each vertex in vertex list, so for each vertex we are going to perform DFS. And while performing DFS, we will count the number of edges. So within DFS, we will count the number of edges and vertices. And once the DFS is complete, we are going to check whether the number of edges and the number of vertices hold the equation which we have just discussed, which is the number of edges should be equals to num of vertices into v minus 1 divided by 2. And if this condition holds, then we will have a count variable or an answer variable, and that answer variable is going to be increased by 1. Which indicates that there is a fully connected component in a graph, and that component we have included it in our answer, and then towards the end we are going to return answer. So let us take an example in order to understand this solution. So let us say this is the graph which is given to us. So the first thing which we are going to do is we are going to represent this graph into adjacency list. So what do I mean by this is, graph will be a dictionary, and then for each vertex, so let us say this is the vertex 1, we are going to form the adjacency list. So from 1 we can just go to 2, so this is 1 will be there. Similarly for 2 we will be able to go to 1 and 7, and then from 7 we are only able to go to 2. Similarly from 3 we are able to go to 4 and 5, from 4 we are able to reach 3 and 5, and from 5 we are able to reach 3 and 4, and from 6 we are not able to reach anything. So this is how we are going to represent our graph in a dict format, in dictionary format. So once we have this info with us, we are going to perform DFS. So let us do that. So the way we are going to perform DFS is, for vertex in range of V. So the number of vertices is given to us, and that info is there in V, and we are going to iterate on vertex. Then we will have something known as visited, whether a particular vertex has been visited or not. And initially for all vertex, the value will be false. And this is for all the vertices. Now within this, we are going to check if this vertex is visited or not. If it is not visited, then we are going to perform DFS starting from this vertex. So let us perform DFS from this vertex. And then let us pass the necessary parameters for DFS. So the necessary parameters are visited and graph. And once we have done that, we are going to check, and let us say over here we will have two variables, which is num edges, and let's say these are global variables. So over here we are going to set num edges equals to 0 and num vertices equals to 0. And then this DFS will increase the number of edges and number of vertices accordingly. And once the DFS has completed, we are going to check if num edges by 2 is equals to num vertices minus 1 divided by 2. So if this is equals, we are going to increase our answer by 1, and towards the end we are going to return answer. Now let us look at this DFS, how we are going to perform DFS. So let's say we want to perform DFS, and a source vertex is given to us, and what all nodes has been visited so far is given to us, and then we have a graph which is given to us. Now with this information, the first thing which we are going to do is we are going to mark this source as visited. So now the source has been visited, so we are going to mark it as true. Then we are going to update the number of edges and the number of vertices. So the number of vertices will be increased by 1, and the number of edges will be increased by length of graph of source, right? So from source, what all vertices can we go to, that information is there in the adjacency list graph, and its length is what we will add it over here. In this way, we will be able to update our number of vertices and number of edges. Now, once we have done that, now let us iterate on the neighbors of the source. So for V in graph of source. So we'll iterate on this, and we will check whether V is already visited or not. If V is not visited, then in that particular case, we are going to perform DFS from V. So let us do DFS from V and visited and graph. So that's the code for DFS, folks. So now let us run over an example in order to understand what we have coded so far. So let's take the graph which we have, which is this graph. So let us say this is the graph which is given to us, and the adjacency matrix of this graph is this. Now what we are going to do is we are going to start from 1, and we are going to perform DFS on 1. Before performing DFS, let us say we have a visited array with us, and initially all its values are false. So this is the state of visited graph, and we are starting from 1. So when we are at 1 and we are performing DFS, so the first thing which we did is we increase the number of edges and number of vertices accordingly. So let us increase the number of vertices. So the number of vertices will be 1 now, since we have visited one vertex, and the number of edges will be equals to the length of 1. So the length of 1 is 1 over here, so the number of edges will be updated by 1, and after doing so, this particular entry will be updated to true. Now the next element in DFS will be 2. So now we are at node 2, and let us update our number of vertices and number of edges. So the number of vertices will be increased by 1, so that becomes 2, and the number of edges, so for 2 there are 2 edges, so this will be increased by 2, and this becomes equals to 3, and similarly this will be marked as true. From 2 we can move to 7, and now we are at node 7, and let us increase it. So the number of vertices will be increased by 1, and the number of edges over here will be increased by 1, so this becomes equals to 4. And after doing so, the DFS completes over here for this component. So once we completed the DFS for one of the component, then we will check the relationship between the number of vertices and the number of edges. So the number of edges is 4 divided by 2. And folks, the reason why we are dividing it by 2 is because we are counting a particular edge twice, right? So if you see over here, so 1 to 2 was already counted. This was already counted, but when we were at vertex 2, we counted 1 again. So because of this, the edge 1 to 2 got counted twice. Similarly, all the edges will be counted twice, because of which we are dividing it by 2. So the number of edges over here will be 2, and then that should be equals to the number of vertices, and 3 minus 1, which is 2, by 2. So this equation does not hold, which simply means that this is not a connected or a fully connected component. Now moving forward, so 7 also, let us mark 7 also to true, and let's move forward. So let's say the next vertex we pick is 3, and over here, so once we start a fresh component, then the number of edges and the number of vertices will be set to 0. Now once we have this, so we are at 3, so the number of vertices will be increased by 1, and the number of edges. So from 3, as we can see, we have 2 edges, so the number of edges will be increased by 2. Now, and similarly in the visited, we are going to mark this as true. So from 3, we can move to 4. So then let's say the next vertex is 4, and then since the next vertex is 4, so this will be increased by 1, so this becomes 2. And the number of edges from 4 again is 2, so this will be increased by 2. So this becomes 4, and 4 also we have covered it. Now the next vertex is 5, so let us visit 5, and accordingly let us update our number of vertices and edges. So this becomes 3, and this becomes 6, and let us mark 5 as true. After doing so, the second component got completed, and now let us evaluate the relationship between edges and vertices. So the number of edges will be 6 by 2, which is equals to 3, and the number of vertices is 3 into 3 minus 1 by 2, which is also equals to 3. So over here, the relationship holds, because of which our answer will be increased by 1, and the answer will contain 1. Now the next node is 6, and 6 does not have any edges. So over here, the number of vertices will be equals to 1, and the number of edges will be equals to 0. And now let us compare the relationship. So the number of edges divided by 2, again, which will be 0, is equals to number of edges is equals to v into v minus 1 by 2, which is equals to 0. So over here also the condition holds, because of which our answer will be updated to 2, and this is what we are going to return. So that's the whole discussion, folks. Now let us see how we have coded this in Python. So the code is pretty much the same as what we have discussed. So over here, from the edge list which is given to us, this is the edge list which was given to us, I'm converting it into the graph, which is the adjacency list. So after conversion, we took a visited array with us, and initially, since none of the nodes are visited, so we are marking it as false. Now we are iterating on the vertex, and we are setting initial value of number of edges and vertices to be 0. Then if the vertex is not visited, we are performing DFS. After performing DFS, we are checking whether the relationship between vertex and edges holds. If it holds, we are increasing it by 1. The answer, we are increasing it by 1, and towards the end we are returning answer. Now the DFS code. So for DFS, the source we are marking it as true, and the number of vertices and edges we are increasing it as we have discussed, and then we are iterating on its neighbor. If the neighbor is not visited, then we are performing DFS on the neighbor. So that's the code, folks. Now let us submit our solution. So our solution got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section, and I'll try to address them. Thank you.